back in the 60s, people first started trying to estimate how many planets would have life in the Milky Way. In particular, in that time, they wanted to know how many could send us radio signals. They did this estimate considering a few conditions, and they came up with a number like a few million planets could have life and could send radio signals. Now fast forward from then 50 years, and now the field of astrobiology and techniques for discovering exoplanets has progressed dramatically since then. And what we find is that the conditions necessary for life are far more than were appreciated in the 60s. And a typical list, a list could have as much as 100 conditions, but even if you take a conservative list of maybe 20 conditions, then each condition has a certain likelihood to be met. You give let's say a 1/10 chance for each condition. And that's actually generous. Some things, the probability of getting that condition met might be way less than a 1 in 1,000. But let's just give 1/10 chance to 20 conditions. That's 0.1 to the 20th power. That's 10 to the minus 20, or less than a millionth of a trillionth. What we then find is that those are the conditions, at least those conditions, that the Earth has met. So the Earth is apparently exceedingly rare, with a likelihood of 10 to the minus 20 to have all these conditions together. Another way of saying it is you'd have to look at tens of thousands of Milky Ways at least before you should expect to see a single Earth. What becomes interesting is as astrobiology matures and we get better and better estimates of the number of conditions and the probabilities, and these probabilities are taking a rapid dive, is that we end up having a priori estimates of how rare it would be to find a planet like the Earth. And so you get to a situation and you say, well, what if, defying it all, we go and somehow devise a kind of astronomical instrument with which we can find life signatures and guarantee that we've seen life. That's already a very challenging thing to do, but let's suppose we did. Then what? Well, if you already know that the probability is very low, and then you see it, what is your conclusion going to be? Let me put it another way. Suppose right from this wall behind me, as we're just talking, somebody just walks through it and just appears in the room. Is your reaction going to be, oh, gee, I guess those things are more likely than I thought? No, you're never going to say that, because you a priori know that that's a low probability event. In fact, impossibly low probability event. And the conditions for life are not maybe impossibly low, but they're getting exceedingly low. So that it should really be surprising, extremely surprising, if we see a planet like ours anywhere within our solar neighborhood. So when we talk about fine-tuning, my favorite one is the cosmological constant, or the dark energy fine-tuning. You see, when the universe started expanding after the Big Bang, it could have had three possible fates depending on the initial mass-energy density. Think of it as how much mass there was, how much material there was, but there was also energy. So the three fates were this. If there was too much mass energy, then the result is that the expanding universe comes collapsing back in a big crunch, and relatively rapidly, so that by this point, there would be nothing to live on. There would be no universe as we know it. The other possibility would have been that there was too low mass energy density, and then this other phenomenon, which we now call dark energy, that we're trying to understand, which we know exists, would have stretched things out so rapidly without the mass energy being able to hold it back, that there would be no opportunity for galaxies and planets to form. And so there would be no galaxies, no planets, no life. And then in between these is this critical mass energy density. And that critical case creates a universe with a condition that we call a flat universe. That's the life permitting case. We find right now that we are in a flat universe condition, give or take a little bit. But then if we ask the question, what would it have to have been at the beginning? What conditions in the universe would have been necessary for us to still be this flat as a universe? Then the requirements are astounding. What we find is that the one source of dark energy that we know, which is this vacuum energy, would have to be canceled to all but a part in 10 to the 120. That's like 1 over 1 with 120 zeros on it at the beginning, for the universe to be flat right now. That's the most amazing case of fine-tuning there is. Okay, there's this great deal of fine-tuning that gave you a flat universe. But then you can ask the question, well, do we really need to have a flat universe? And it turns out you do, because either in the rapid expansion, where the alternatives are a rapid expansion or a rapid coalescing of the universe. In the rapid coalescing, which is from having too much mass energy, you certainly do get stars and planets, but you get them very rapidly, very energetic stars, and they fizzle out very rapidly, long before this time period in the universe's age. In the other case, where you're not flat, but you're actually accelerating, then what happens is everything is coming apart too quickly for any aggregation to form, any protoplanetary disks, and any stellar formation. So you get no stars, no galaxies, no planets. So here I am, a person who has invested now 20 years of his life in the search for extrasolar planets, and yet I talk at the same time about Earth-like planets being rare, and how do these reconcile with themselves. And the point is this, that the study is absolutely fascinating, it is extremely illuminating and enriching. And between me and my colleagues, I think we would not always be in the same place. I think, Earth-like planets are rare. Many of my colleagues don't think they're very rare. But I think that we all collaborate on making the most sensitive instruments to detect such planets. And in the end, what we're going to hopefully find is that we have instruments in which we have confidence that if we were able to see one, that if there was a planet that met all the conditions of being Earth-like, we could have observed it. And what then we observe will be subject to interpretation and subject to a careful scientific and philosophically well-balanced analysis. And I think that the fact that there is a plurality of points of view helps all of us to keep ourselves honest and to think soberly about these conditions. In my case, I think that what we're going to find is we're going to learn a tremendous amount about planet formation. We're going to find out even more about how fantastically fine-tuned this planet of ours is, and then we're going to also see many other planets. I just happen to think that probabilistically we're not going to find planets with life like ours abundantly anywhere near our solar system. So when we think about all that we've seen now with the ground-based and space-based observatories, it is really a spectacular harvest of exoplanets around other stars. And what have we learned? Well, we see a very large number. The ground-based radial velocity technique has given us this large harvest of Jupiter-mass planets. A lot of these planets have the characteristic, though, that they are, a lot of them are in these highly elliptical, high eccentricity orbits, and then many of them are also in these tight circular orbits around their host star. So this tends to, what the picture that it has basically given us is that in the majority of systems, what you have is these high eccentricity, very large gas giants that have the ability to be very disruptive. And these migrate inwards and totally disrupt the inner planets where, like, for example, the Earth would be. So in that sense, the Earth came off really, really lucky because in our case, all of our gas giants, like Jupiter and Saturn, they're in almost perfectly circular orbits. The Jupiter's at 5 astronomical units. That's 5 times away from the sun as we are. And so it is just politely sitting there in a perfect circular orbit, cleaning up the debris of the solar system for our benefit, and providing a very rare, by the view that we have from these exoplanet discoveries, a very rare kind of stable, clean environment for the Earth. The other thing is when you look at the Kepler planets, you see that the great majority, the vast majority of these are very close in to the host star. Now the Kepler technique, which is a transit technique, is looking for the obscuration of the starlight as a planet goes in front of it, transits in front of it. Now you can imagine as the planet goes far from the star, the likelihood that you would catch it goes down. So there's a bias in the measurement to only see the planets that are close in and miss the ones that are farther out. But you can calculate what that bias is. And when you even correct for that bias, you still see that in the majority of cases, even more than this detection bias, that the exosystems are all filled with planets that are very close in. Planets that are too close in are typically not in the habitable zone. The other thing is that most of the planets that Kepler has seen are around M dwarfs. These are cooler stars, redder stars. The habitable zone for M dwarfs is very close in relative to our energetic G-class star. What is the consequence of that? If you're so close, if your habitable zone is that close to the host star, now you are in this dangerous tidal lock radius. You're inside of the tidal lock radius, where the planet's orbital period gets matched to its spin period. And so the same face of the planet is constantly exposed to the star. One side boils off and just desiccates, while the other side, it basically snows down. And as a result, you have more or less a desiccated, very inhospitable planet, nothing remotely like the habitability of the Earth. So with regard to the Big Bang, by now it's one of the very well-established, one of the best established astronomical findings. And people's reactions to the Big Bang has been kind of all over the place. People who are theists might have thought at one point that this might be some theory concocted by atheists to come up with something that basically is negating some picture of creation that they might have had. But in fact, historically, it was sort of the opposite. About 100 years ago, Einstein's general relativity came out. It was in 1915, just a little over 100 years ago. And it was, interestingly, at that time, Einstein was almost embarrassed about one of the solutions to his general relativity result, which was that the universe is dynamic, that it could be either expanding or contracting. And in fact, what we now are very excited about, which is the cosmological constant, was a fudge factor that he actually introduced into the equation because Einstein, like his colleagues, who were essentially all atheists, had wanted a static universe, an eternal universe. If the universe is eternally long, in existence, sort of like Carl Sagan saying the cosmos is all there is and all there was and all there ever will be. If the universe is static and has been there forever, then any notion of a creator can be relegated to eternity past, and we don't have to really think about it. So it was that was the mentality. In fact, Arthur Eddington, who was Einstein's friend and eventually was the one who, through the eclipse observation, actually in a spectacular way proved that general relativity was correct, famously said that he found the result, the idea of an expanding universe, which we now attribute to the Big Bang. He said he found that philosophically repugnant. This is just interesting. And so anyhow, the history of 20th century astrophysics is one of a lot of reluctance to accept this Big Bang model. In fact, Big Bang itself was a derogatory term that was, I think, coined by Fred Hoyle to sort of put down this idea of an explosive beginning to the universe. You know, the field of exoplanets is only now, what, 23, well, you could say it's 23 years old since the first discovery that has been was confirmed. And as time went on, and also as astrobiology matured, and is maturing still, the inference that you can make from observations is beginning to morph from one type to another. If you're coming fresh into a field of study, just your observations tend to tell you what is likely and what's not. What you're observing, it tends to be, you consider that likely, and what you're not observing is unlikely. And that's all good, and that kind of guides your theory. As things mature and you have a theoretical basis and then you've got many more observations, you're now beginning to actually have a prejudice. You are now having not a bad prejudice, but you have a sort of a seasoned scientific and philosophical framework with which to judge what you're observing. In a way, it's like this. If you are walking down the beach and you see a little buildup of sand that looks just like a little pileup, you may not think of it as anything remarkable. But now if this pileup looks more cylindrical, it starts kind of raising your curiosity. Because now you have a priori notions of how likely is it for waves to generate something that looks like a vertical cylinder. Now if you see little turrets on the top that looks like a little castle, now your a priori feelings about or estimation that's going on in your head, you're going, that's not waves. And in a sense, that's what's going on as we keep going forward in the exoplanet and astrobiology, kind of moving away from the place where an observation of an exoplanet teeming with life right near us would have us say, oh, gee, that must be easy. No, we already know it's hard. It's just like the guy with the sandcastle. He's not going to say, oh, gee, I guess sandcastles are easy to make by waves. No, that a priori knowledge that he's accumulated of what waves can and can't do tells him what mechanisms he needs to rule out when he sees the sandcastle. And in the same way, now if we ever see an exoplanet with life, we now know a lot more about what chance and materialistic processes can and can't do, and what is required for life to be there. And the way we're going to analyze that is going to look different.